So before going through the example from Alex, I'm going to use a few examples from the worksheet of the day. That way I can help you to complete the worksheet of the day. On the worksheet of the day, the first exercise that you are seeing is from the mental math warm-up. You have this quadratic equation, and it is indicating to use the quadratic formula to solve this quadratic equation. So let me go and put here the quadratic equation. Okay. And we have seen two methods to solve this type of quadratic equation. One by the quadratic formula, and the other one by doing a factorization first of this quadratic equation. Okay, so what's the problem? Why do we, or why the world instruct us to use the quadratic formula here and not to go and do its factorization first, the factorization of this quadratic equation? Why is that? Anyone knows why we need to use the quadratic formula and not do the factorization of the quadratic equation first? Any idea why use the quadratic formula instead of going through the factorization, which seems to be easier, because if we multiply something by 0, everything is going to be 0. Okay, so let me help you here. We might want to try to find a factorization, right? Two linear factor of this quadratic equation. What would be the problem? Well, the option that we have here for -1 is going to be 1 times -1. So there's no much that we can do there, right? We can play with the first terms of this linear, right? Our goal now is that if we add these two and we multiply first the inner one and then the outer ones, and we add them, we need to have positive 2x. But that's not the case with this scenario here, right? It won't be, if we expand this, if we distribute what we have here, we are not going to get this same exact equation. Okay, and you will notice that there is going to be impossible right now with what we know to find the two linear factor of this quadratic equation just by going through this method, the trial and error method. So this is not possible here, and this is something that you need to keep in mind. It's not going to be always possible to find a direct factorization of the polynomials. If that's the case, then we need to go through all the properties in order to find the zeros and the linear factors, right? Some polynomials, we can use the technique that we know as foil factorization or group factorization or so on. Okay, they are techniques that shorten the path through a standard form and the factor form of any polynomial, but those paths or those techniques are not always going to be possible to be used based on the polynomial itself. So in this exercise, we need to use the quadratic formula directly, and there's no other options at the moment because there's no way to find two linear factors of the polynomial that we have there, as it is right now. When we do the quadratic formula, we got the zeros, and hence we are going to get the linear factor. But going through the technique that we know so far, using the technique that we know so far, is going to be impossible to find those linear factors. So here we use the quadratic formula. We solve this. So 4, 16. I think this is 20. Okay, so look the focus on this. That's the result. There we are seeing two different values when we use the addition operation and the subtraction operation. What we have here, we have a number that is going to be very difficult to put in a simplified version. I believe this is what we have here. It could be a rational number. Yes, we are seeing a fraction, but you are seeing that the numerator has two terms, -2, and the other term has 2 times square root of 5. Then there's no way to simplify these two values here. In order to get linear factors, we need to have the zeros, right? Why it is impossible to go to the direct path from standard form to the factor form? Well, because we are not going to think of this kind of numbers in order to find the linear factors. Hence, or that's why we use the quadratic formula in this scenario. Because, I don't know, if you think of number in this way, well, that's good for you. But we are not used to think in values in this way. We are used to think in whole numbers or natural numbers. Okay. So that's the reason why here you want to use the quadratic formula instead to find the linear factor by force. All right. Any question on that one? Okay. The other one that I'm going to use to discuss more topic about or more details about our unit is this polynomial that is here. All right. Okay, so right now our goal here is going to be to factor this polynomial. As you can see, this is a degree of 3 polynomial. We are seeing all its terms and we have the standard form. Okay, so let's try to do the factor form by force. When I say that, let's try to not go over all the properties of this polynomial. Let's jump right over to find its factorization by a factorization technique, because we are working with a degree of 3 polynomial and we have 4 terms. Here we can try to do factorization by group, where my groups are going to be the first 2 terms and the second 2 terms, right? So first group, there it is, and second group. All right. From the first group, can I factor out? Is there a common factor from the first group, from the 2 terms that are in pink? Is there a common factor there. X, Richard, that's correct. More correct is x squared, Amanda. Yes, Richard, we have in two terms. One has 3x's and one has 2x. So we can take from both 2x. So x squared, 2x, x squared. From the second group, do we have a common factor? It is 3. So 3 on the first term, and 9 has to 3 squared, or 3 times 3. So we can take 1 3 out from there, and what is left is just 3. Now we are seeing a common factor within the terms, and that common factor comes in a form of a polynomial or a linear polynomial. So we can factor out x plus 3, there you have it, times what is left from the first term, x squared, and what is left from the second term is 3. And that is going to be the factor form of this polynomial. See that here we could use the factorization technique of group factorization, and whenever we have this opportunity, we are going to go to this route. Okay, if we want to find the zeros, help me here. What are the zeros of this polynomial? Now that you have the factor form, what are the zeros of this polynomial? Okay, help me to solve the following equation. What are those zeros? 3 is 1. No, 3 is not 1. Sorry, Amanda, I thought you said something. But let's go back. Help me to identify or to solve this equation. What are the x values that makes this whole equation equal to 0? Do you remember how to do this? Okay, I like that I am seeing 3's, and I like that I'm seeing -3. Okay? The factor form in this scenario help us because we can split the exercise into multiple pieces based on the factors that we have. Okay? I can drop the parentheses here. So we have a linear factor and we have a quadratic factor. From the linear factor, we subtract both sides by 3, and we got that x is equal to -3. So that's one of the zeros. Okay, and that makes sense because we have a linear factor and see that the opposite value of +3 is -3, and we got it. What's the problem with the second factor? The second factor is not linear, it's a quadratic factor. In this case, you want to do -3 on both sides, and what you are left is with x squared equals -3. Is there a problem here? Can you tell me if there is any issue with the equation that we have here? It is not a problem. Go ahead.
Isn't it that to get rid of the x running with 2, you have to square root x, but you can't square root -3, so it would be I?
Will we just say odd, or is that what you said, odd?
No, like I, like imaginary.
Yes, that is going to be the issue here. The issue here is that if you are using your, sorry, I thought you said something, right? Okay, never mind. The issue here is that our calculator is set based on the real numbers. If we are just exclusively working with real numbers, we are going to say at this point no solution. Okay, but the real answer here is no real solution. Okay, like you said, it's going to be now we are going to be working in imaginary numbers, with imaginary numbers. Okay, so at this point, yes, we can cancel out the power of 2. So now x is going to be plus and minus a square root of -3. We can simplify this as plus and minus 3i. And there are the zeros. Okay? So those are the zeros of the other two zeros of this polynomial. Positive and negative 3i. At this point, you might wonder, wait, we know that if we have a 0, we have a direct linear factor. And this here, we have two zeros, positive and negative 3i. And yes, we can get linear factor from those numbers. That means that this quadratic factor could be factored as, let me put it here, the first factor is a linear factor, right? X plus 3. But now, x squared plus 3 can become x. Here, remember we have two plus and minus. So x minus positive 3 is going to be negative 3i, and then x minus negative 3i is going to be x plus 3i. Okay, and we have went further on the factorization of our polynomial, putting its factorization or its factor form in all linear factors. Depending on the polynomial, we are going to have linear factor with real numbers and other linear factors with imaginary numbers. Okay, anytime you have a quadratic factor with a positive constant value, you will end with two imaginary linear factors. The goal is to write the factorization of a polynomial in all linear factors. Okay. So look how we did this by factorization techniques. Okay, just we use a little bit of properties of the zeros here to go and find the two other linear factors. But by this point, we use only the technique of factorization by grouping. Okay. That was possible because of the polynomial that we have here. But there are other polynomials that is not going to be possible to do this technique. And hence we need to go through all the properties. And here is the important thing from unit number 6. We are going to learn the techniques or we are going to learn how to use the property of the polynomial to find all the zeros and all the linear factors. Okay, so I'm going to use this exact example, but now I'm going to solve and I'm going to reach this factor form by the properties that we are going to learn from unit number 6. Okay, and what I'm going to do is going to help you to complete page number 2 of the worksheet today. Okay, because that is this steps here is the step that I'm going to follow, and this step here, page number 2 of our worksheet of the day, it is so important because this is what you need to have in your mind whenever you are working with this type of exercises. When you have a polynomial and the goal is to list all the zeros of that polynomial, okay? List all the zeros and to write all the linear factors, okay? So you have exercise number 4 is the exercise that you are always to reference to do all the exercises on unit number 6, because here you have all the steps that you are going to follow, and I'm going through all these steps, okay? And we are going to compare all these steps with the group factorization method, okay? All right. So first thing that we are going to identify is the total of zeros, and see that I am not using total of real zero or complex zeros. Total of zero, when you see total of zero and the zeros, it's not I specify what type of zero we are looking for. We are going to assume that we are talking about the real zeros and the complex zeros. Complex zeros is another way to refer to imaginary numbers. Okay, complex is like all the zeros, right? Yes, no. Well, maybe I might be wrong. I need to double check that. But another way to talk about imaginary numbers is referring to as complex numbers. Okay, so the total of zeros of any polynomial, real and complex, is going to be the degree of that polynomial. So the degree is 3. Total of zeros are going to be 3. This first step, it is important because it will guide you through your objective. If the exercise is to find the zeros, all the zeros, you know how many zeros you need to find now because of the degree. You need to find 3 zeros. B. Find one rational zero. Okay. See that what I'm doing here is laying out the strategy that you're going to follow. Okay? First thing that you're going to do is to identify how many zeros you are going to look for. Then we don't know those numbers yet. But we at least want to find one rational zero. One rational zero. Why a rational zero? Because we have a theorem of possible rational zeros. What does this theorem says? It says that we can create a list of possible rational zeros based on the leading term and the constant term of any polynomial. The leading term here is 1 because there's nothing there, so that's the leading term. The constant term here is positive 9. Okay. So we have leading coefficient. Leading coefficient is 1. Constant coefficient or constant term value is 9. How are we going to use those numbers? we need to identify their factors. Okay. So what are the factors of 9? Can you tell me the factors of 9? Remember about what a factor is. Three is one. 3 is one factor. Any other factors of 9? 9 and 1. So 1 times 9 is 9. So 1 and 9 are factors. So 9 is a factor itself. And 3 times 3 is 9. So 3 is a factor as well. What are the factors of 1? Factor of 1. What are those factors? The factor of 1. Just 1. 1 times 1. Okay. From the polynomial, we got the constant term, the leading coefficient, the constant term value. Then we got the factors. Okay. We are going to create a list of possible rational zeros. Okay, the key word here is possible. All right, so how are we going to create the list of possible rational zeros based on the factor of the constant value and the leading coefficient? So you are going to remember the following. The constant term is going to be represented by the variable p, and the leading coefficient is going to be represented by the letter q. Okay, representation. Now we are going to create a list of p and q. Okay, p is representing any factor of the constant value, and q is any factor of the leading coefficient. Okay, so I should just copy and paste this. Okay, so now we are going to find all the possible combinations. Combinations. How we are going to create those combinations? Well, we are going to start 1. So I'm going to create a set here. Okay. So that's why I'm using the curly brackets. It will be 1 over 1. Okay. It will be, that's just 1. The good thing with the exercise is that with the leading coefficient is just 1, so basically we are getting the same exact values from the factor of the constant value. Okay, you will see on other exercises where the leading coefficient is now going to be 1, and then we are going to do other combinations. But right now, what you are getting here in this list is the possible rational zeros. Any questions so far? Okay. Critical thing that you need to know here. This is the list of possible rational zeros, but you need to remember that we have different type of zero. We could have rational zeros, we could have irrational zeros, and we could have complex zeros or imaginary zeros. So it will happen for some polynomials that you are going to create a list of possible rational zeros, and none of those numbers are going to be zeros of the polynomial. This is just a list of possible rational zeros. Okay, it could happen that you create the entire list, you go through all those numbers, and you are not going to find a zero, because that means that polynomial does not have any rational zero. It has or rational zero or complex zeros. All right. Now that we have this, why do we want to find just one rational zero? We need to find one rational zero at least. The first step of step number 2, or B, so B.1, is to use the theorem of possible rational zero and to get the list, right? Then, what you want to do with the list is to not go through all those, just to find just one zero. And here you have multiple methods to determine which of these three is an actual zero. Okay, you could use the graph, and the graph is what you want to use. Okay, the most easiest way to identify a zero from the list of possible rational zeros is by going through the graph of the polynomial, and we are going to do that because our calculator, you have a graphing calculator, and you don't want to waste time of testing any of these numbers from the list. The other thing that you can do is that you can use these possible rational zeros, so you can plug in one. I believe this polynomial is called G. Okay, if 1 is a zero of the polynomial, when you plug in 1 there, the value of the function is going to be 0. So that's a second method to determine which of these three is 0. So that means that you need to go and plug in 1 into the function, 3 into the function, or 9 into the function to find if there any 0. So now you can start imagining, well, here we have just 3 possible zeros. What happens if we have 8, 16 possible rational zeros? You don't want to waste all that time at test. So you're not going to use that one. The third one is the least one that you are going to use, is where you are going to use synthetic division. Okay? And if you are going to find a remainder of 0, that one means that you are going to create a linear factor from, or a linear polynomial from this possible rational zero. For example, you go and take 1 positive. Well, you are going to create a linear polynomial of x minus 1. And then you will go and do synthetic division between x minus 1 and the polynomial. Okay? And this polynomial. And if the remainder is 0, then it means that the value that you selected is an actual 0. Too much time there. You are not going to do that one. Okay? So you know 3 methods to identify which of these numbers. That's okay, Tristan. Okay? Which of these 3 numbers is an actual 0 from of the polynomial? But you're not going to go through method 2 and 3. Let's go to a graph. Okay, so what you are going to do at this point? Let me see if I can do the graph here. Can I just write the function? Let's see if this helps. I don't know. You can go and use your calculator and put the graph, type the polynomial in your graph, so you can see your graph in your calculator. Yeah. So that's what I have here. Okay. So what we are looking here, what we are looking at here, what you have on the right is the graph of the polynomial that we have in our exercise. Why do you want to go to the graph? Because from the graph you can identify, if I can select this correct, from the graph you can go and look if there are any rational or real zero. Okay. Here is the graph of that polynomial, g of x. That's the graph. In the graph, you need to remember the coordinate plane, we are going just to see real zero. If the polynomial has real zero, then we are going to see x-intercepts. Here is the x-intercept. The x-intercept has a value of x equal to -3. -3. I forget to say something about this. We are going to consider the plus and minus, not only the positive side. We are going to consider also the negative and the positive value for this. Rachel, you won't be able to use Desmos because of the lockdown browser. I can explore with you what other options you have after I finish the class. Okay? Yeah, because if you don't have a graphic calculator, just stay after class to see what options you have to use to use a graphic calculator. I think you might be able to use the calculator that the operation system has, but we will check. Okay. So I forgot to tell you that in the combination of positive rational zero, we're going to consider the positive and negative. Okay, so that's important that you need to consider. Okay. From the graph, you can now be certain that yes, there is at least one rational zero. Well, there is only one rational zero because we can see from the graph that there is just one x-intercept. So that means that there is just one rational zero, a real zero here. So it is -3. Okay, so this is what you want to do here. After you do the list, you don't want to go through all the numbers, go straight to the graph, and you are going to identify that any real zero is there, any. Okay, so we are still in the step where we want to find just one rational zero. Why do we want to find just one rational zero? Because now is the important part. Because here is where we are going to find a depressed equation. I'm going to explain to you just in a moment what a depressed equation is. And also I'm going to here we are going to use synthetic division, and I'm going to take advantage of this step to show you the method that I do to do synthetic division. Okay, let's review. Okay, it is, I know, it is we need to a lot of pieces that we need to follow in the correct order, and we need to be certain of each of these steps in order to get to the correct answer. Okay, so that's the problem of these units, that we need to go through a lot of process in order to get the correct answer. From the polynomial, we can get how many zeros we are looking for. 3. 3 because the degree of this polynomial is 3. That's step number 1. Step number 2. We need to find, the goal of step number 2 is to find at least one rational zero. Is there any? There are going to be some polynomial that there is not going to be any rational zero. And that is going to be other thing to do. But in this class, we are not going to focus on polynomial with no rational zeros. Okay, so for this class only, all the polynomials that you are going to be working at least will have one rational zero. If there's no rational zero in that polynomial, the exercise is going to tell you something different. It's going to give you other information that you will use. Okay, but that is going to be the minimum. On the test, you are going to get polynomials with rational zeros, with at least one rational zero, right? Because we know that we have at least one rational zero in those polynomials, we are going to do the list of possible rational zeros using the constant term value and the leading coefficient value. We create all those combinations, taking into consideration the positive and the negative value of those values. And then from the list, we are going to determine which of those numbers is a rational zero. To do that, we are going to do the graph. The graph is going to help us to identify the rational zero, at least one, because an x-intercept means a zero. Once we got one rational zero, I think, yeah, we have done that. So, sorry, this is going to be step number C, the third step. Okay, so we have finished with our goal of the step number 2, which is find one rational zero. We have done that. Now, we are going to use that rational zero that we have, which is -3. Okay, so I'm gonna put it here. I know that our rational zero is -3. Because of that is a zero of the polynomial, we know that x plus 3 is a linear factor of that polynomial. Okay, 0 factor. Okay, rational zero, linear factor. Now, what is the difference equation and why do we need to do synthetic division? What we are going to do at this step is that we are going to divide the polynomial by its linear factor. We are setting that x plus 3 is a linear factor of the polynomial. So we are going to divide that polynomial. Okay. How do we do synthetic division here? Okay, the first thing is that I'm writing division in this way, but we also can write it as a fraction. I'm going to write as a fraction normally, but here I just want to show you just the formal structure of division, right? So that means that we are going to divide the polynomial by this linear factor, dividend and divisor. In a fraction, you will see it this way. Okay, all this is the same. All these are equivalent things. We just using different form to write division. Okay, the important thing is that the denominator here is the linear factor. Synthetic division. How are we going to do synthetic division? First thing that you are going to do, you are going to take that the 0, which is -3, okay, you can see that in the linear factor we use the opposite value, okay? But you are going to take the -3, and the -2 is going to be outside of the pseudo rectangle here in the synthetic division. What are you going to do next? Then you are going to select all the coefficients of that polynomial. And here it is an important detail. This polynomial contains all its terms, 3, 2, 1, 6, and 9. Remember that if you are missing one term, that means that the coefficient of that term is 0. You need to take into consideration all those coefficients. If there is one term that is missing, you need to fill that space when you do synthetic division with a 0. Okay, so synthetic division is a simplification of long division, because see that here we are just going by the constant term of the denominator and just the coefficient of the numerator. Now, what are you going to do? Down, we add. So 1 plus 0, there's nothing there, 1. Going up, we multiply. Multiply what? -3 times the value that we have here. So -3 times 1, -3 there, right? Again, down, we add 3 times -3, or 3 plus -3, 0. Going up, we multiply. What we multiply? The value that we have here times the 0 that we, or the value that we have outside the rectangle. -3 times 0 is 0. Going down, we add 3 times 0, 3. Going up, we multiply. What we multiply? This 3 times -3, -9. Going down, we add. And then we are getting a 0 here. From here, there are two groups that we need to take into consideration. The last number that we are getting is the remainder. The three numbers, in this case, are 3, but all the numbers that we get on the left side are going to be the coefficients of the quotient equation, of the depressed equation. I'm going to explain the depressed equation just in a moment. Okay? We're not done yet. Let me stop here. Having a 0 here is important. Having a 0 here confirm that -3 is indeed a 0. So this here is important. You are not getting 0 here after doing this integration. That means that the number that you selected is not a 0, or you did something wrong in the synthetic division. Okay, so this 0 is important. You want to have this 0 here. Maybe I have it phrased there. All right. Any questions so far? let's talk about the depressed equation and what is a depressed equation, why it's so important. Now, depressed equation means that we are going to get well, maybe I depressed equation is going to be the quotient after the division, but we remember that we need to remember that we are dividing a degree of 3 divided by a degree of 1. Okay? Degree of 3 divided by a degree of 1. So in this scenario, when we get a quotient, the depressed equation is going to be a polynomial at 1 degree less polynomial. Okay, it will be a 1 degree less polynomial. So we went from a degree of 3 to a degree of 2. Because you can think of x of 3 divided by x. In this case, we subtract the exponent. This is not a formal explanation, okay? But you can relate degree of 3, degree of 1. We subtract the number of those degrees and we get 2, okay? This is the law of for exponents, okay? This is something that will help you to remember. Okay, so the depressed equation is when we do a division of polynomial and then the degree of that quotient is 1 degree less. In this scenario, is 1 degree less because we are dividing by a degree of 1. Okay. Why is it important to have a degree of 2 now, a degree less? Is because you can think of a level of difficulty. The easiest polynomial to work with is the linear one, degree of 1. The second easier one is the quadratic equation. We did that on unit number 4. We learned about quadratic equation. Number 8, that's degree number 2. Now we are working with in general polynomials, and you can see that degree of 3 is more difficult than degree of 2. The same way is going to be for degree of 4, it's going to be more difficult than degree of 3. And so on. The higher the degree, the more difficult it is to work with that polynomial. So that's why we want to go and do the depressed equation, because getting that degree lower is going to help us to continue working with the polynomial itself. Okay, so now our degree, the degree that we are going to be working with is a degree of 2. And what happened with that is that from the degree of 3, the polynomial degree of 3, we have identified 1, 0. We have divided that polynomial by one of its factors. So we have a depressed equation that continues carrying over the numbers of zeros that we have in the first place, with the only difference that the zero that we use, the zero that we use to divide and to get the depressed equation, that's something that is not going to be repeated. It's not going to be carried over to the depressed equation, but the other two remainder zeros, okay? So we found one rational zero. The other two remainder zeros are contained in the depressed equation, and that depressed equation is a degree of 2. Degree of 2, that depressed equation has a total zero of 2. That has a 2 zeros that we are going to find, and those zeros are the same for the linear one. Bit complicated, yes. A lot of practice is going to help us to get through all these concepts. Okay, so how are you going to use the depressed equation? Take these numbers that you are getting here, okay, and remember, we are getting from a degree of 3 to a degree of 2. So this is what you are going to do. My first number is the leading coefficient of the depressed equation. The depressed equation, I'm going to use q of x. The depressed equation is 1 times x squared plus 0 x plus 3, and 3 is going to be the constant term. Okay, you can see here the constant term is going to be always the one that is next or before the remainder, and the leading coefficient is the number that you are getting first in the synthetic derivation. From here, now we don't need to go and work with the original. I'm going to simplify this. We don't need to go back and work with the degree of 3 polynomial. Okay, we are not working with the original polynomial now, because we have found just 1 0 from there, one of the 3 zeros that we need to find, and we don't want to go back and work with a degree of 3 polynomial because it's more difficult than working with the polynomial that we have here, which is a quadratic equation. It is a quadratic polynomial. It's a degree of 2 polynomial. It's 1 degree less, so it's easier to work with. More importantly, the properties from the original one are carried over to this one. Those properties are those 2 zeros that we need to find. Those 2 remainder zeros that we need to find are in this polynomial. Degree of 2, how many zeros does this polynomial have? 2, because its degree is 2. So those zeros of the zeros of the depressed equation are the same zeros of the original one. Okay? So you want to repeat this process. You want to repeat all this process until you reach a depressed equation of degree of 2. Why you want to do that? Because now we have techniques that help us to solve a quadratic equation. Because what we need to do now, we need to find the zeros of the depressed equation. Okay, so what we need to do in this case, this is a quadratic equation, but it only has 2 terms, so we don't need to do the quadratic formula. We need to do this, and look what we are getting. We are getting x plus minus 3i is the same that we got here, right? So if our goal was to find all the zeros, we have done that, because here we have 2 zeros, and the other one that we have found is negative 3 is 1 0. So in total, we have the 3 zeros of that polynomial. A long explanation of all the process. Now I'm going to do more examples where I'm going to do not go deeper into the explanation. I'm going to show you more a practical way of how you are going to be solving these exercises, and that will help you to understand this better, because all the time that I have taken here is to make sure that I'm telling you all the aspects that you need to know. But once you are good with those aspects, all those theoretical part of that knowledge, the mechanical part gets easier. And that's what we are going to do just in a moment. Okay, I just want to iterate once more time all these steps. And also, I want to show you the difference between the factorization techniques versus going through all the steps. On the factorization technique, this is all what we need to do. all what we did, just these steps are here. Going through all the properties, see that there is more work to do. At the end, it's the same process. What you want to do to become a efficient professional is obviously to do things in the easiest way. Always you are going to find optimal ways to solve problems, real problems. In order to find those optimal routes or paths, you need to get all the knowledge before. So you are sure that your path, your routes, your methods are correct. Okay? So that's what we are doing here. In our math class, you are getting all the knowledge. You are getting all the theoretical knowledge. Then, on your future, when you are a professional, you are going to apply that knowledge, but in an optimal way. Okay? Justin, I believe you have a question. Okay. All right. What else do we have to do here? Okay, so this whole process is going to help you to do page number 2 and first part of page number 3 of the workshop of the day. Okay. Amanda, send me an email and we set up a time. Okay, all this process that I just discussed is all this. Okay. The next exercise, you will see that you are going to be working with a degree of 4 polynomial. So that means that you need to iterate to the complete process few times, 2 times to be precise, because the first iteration is going to give you a degree of 3 polynomial. So the first equation is going to be a degree of 3. Then you will need to repeat the process to get a degree of 2. And once you get a degree of 2, then you can apply the quadratic equation properties. Okay? But what I just explained, what you have on page number 2 and on page number 2, that process you need to do it twice for exercise number 5 because the degree is 4. So you need to go downgrade this degree to a degree of 3 and then to a degree of 2. The amount of zeros that you have here for this polynomial, you have 4 zeros. 2 of those zeros are real zeros because you have its graph here and you are seeing that only has 2 real zeros. That means that the other 2 zeros are going to be imaginary zeros or complex zeros. Okay. What else am I missing here? I think that's it for the steps. One thing that is going to be tricky sometimes is going to be to know what is the exact leading coefficient. Well, the leading coefficient, you can get it from the standard form, right? But sometimes careful because it could happen that you are going to factor the leading coefficient at some point. Okay, and if you cancel that factor, the leading coefficient could be lost at some point in those process. The easiest way to know the leading coefficients going back to the original one and taking it from there. Okay. All right. So let's see what is a good exercise to go through this. Okay, class, what do you want me to do? A degree of 4 or a degree of 3? which one do you prefer to do here? That will help you to understand this process, and then we can practice more. So I have this one, which is degree of 3, where we need to do all those processes, and I have this one, degree of 4. Okay, I am seeing here degree of 4 from Rachel. Okay, I think this is going to be the smarter exercise to practice, a degree of 4, because it's the most difficult. So you will have a video doing a more difficult exercise, and that I think that will help you to do other ones. Okay, I believe we are going to have time, and we can do the degree of 3 as well. Okay, I'm going to start with this one, and I'm going to ignore what Alice is asking for. I'm just going to focus more on the exercise and to go through all the steps. Let me just check that I'm getting the correct answer. Well, we'll see what happened with this one. Okay, but we are going to go through all the steps. All right. I am not 100% sure that we are going to be able to find all the zeros, and that's going to be because we could have rational, irrational zeros. Okay, if we have irrational zeros, and there's sometimes we could get stuck in the process because of the technique that we have available on this class. Sometimes if we have irrational zero, we could get stuck. Okay, this exercise is not telling me that there is any rational zero. Okay, a lot of exercises in Alice is going to tell you at least there is one rational zero, and that for certain will help you to find the other ones. But that's okay. Let's practice all the process, and let's go and see if we can get the 4 zeros. The first thing that you need to know here is that you have a total of zeros of 4 zeros. You know that because of the degree. Okay. Second, see that I'm doing this in short steps or writing. Second, list of possible rational zeros. So you are going to get P for 9. So I'm going to use P is going to represent the factor of 9. So 1, 3, and 9. And Q is going to represent the factor of 2. So 1 and 2. So the list of possible rational zeros, I'm going to put the plus and minus here outside, so we don't need to write plus and minus for each element here. So 1 over 1, 1. Okay, 1 over 1, 1. 3 over 1, 3. 9 over 1, 9. Now, 1 over 2, 1/2. 3 over 2, 3/2. 9 over 2, 9/2. Those are the possible rational zeros. Okay? Now, we need to find at least 1 0. At this point, you will go to your calculator, and we'll put that in our graphing calculator. Four minus 3 okay. Okay, so based on this, I can tell you this is the graph of our polynomial. From here, I know that 1.5, 3/2, is in the list of possible rational zeros. So I know that 1.5, did I write it correct? 1.5 is a rational zero. Look at the other one. 1.89, but you can see that I cannot get 0 exactly. That means that but the other x-intercept is going to be a rational zero. Okay, and that's going to be a problem in our class because we don't have method to work with the rational zeros. Okay, but that's okay. Let's just focus on the rational zero, and let's do all the process with this rational zero, and then let's see what happens. Okay, so from this one, I know that 3/2 positive is the 0. So the linear factor is going to be 3/2. X minus 3/2. So what I'm going to do? I'm going to do synthetic division. And from here, let me just copy this because I will need this. Okay, that is the polynomial. And there is something missing on this polynomial. There is one term that it is missing. That is the term with x, just x. Okay, so that is something that I need to take into consideration when I do synthetic division. So plus 0x. So my coefficients are 2, -3, -4, 0, and 9. Those are my coefficients. Now, let's apply the properties here. Going down, we add. Going up, we multiply. 2 times positive 3/2, that gives me 3. Okay? 2 times 3/2, we cancel the 2 and we got 3. When we add, we got 0. 3/2 times 0, 0. We add, going down, we got -4. Now, 3/2 times -4, we cancel this 2 with this 4, so it's the same as 3 times -2. That gives me -6. Alright? We add and we got -6. 0 plus -6. We go up and we multiply. 3/2 times -6. We cancel this 2 with this 6 and we got 3 here. So 3 times -3 equals -9. Going down, we add and we got 0. And this 0 is important because this is the remainder. And the remainder is telling me, yes, 3/2 is indeed a 0 of this polynomial. And we knew that before because of the graph. Now, from here we get the depressed equation. The depressed equation will have coefficient of 2, 0, -4, and -6. From 4, we went to a degree of 3. So minus 4x plus 6. You can simplify this as 2x3 minus 4x minus 6. And that's the depressed equation. The number of zeros that this depressed equation has is 3, because its degree is 3. We needed to find 4 zeros. We got 1. One of those zeros is 3/2. Okay, so we need to find 3 more. Those 3 more are here. I'm not quite sure that I'm going to be able to find the other zeros using the method I just showed you, because the other zero that I have here is an irrational zero, and the other 2 are going to be complex zeros. Okay, so at this point I'm going to try other thing, but if I'm not able to find that, it's going to be okay, because you are not going to be working with this type of polynomials. All the polynomials that you are going to be working are polynomials with rational zeros, rational and complex zeros, and that will lead you to find those zeros. So you can see here right now, I'm gonna stop there. I'm not going to talk about method to factor this one, because this is beyond our class. Okay, but what is important here is that we went through the process of total zeros, the list of rational zeros, 1 0 using the graph, and the depressed equation. And this is all what you want to do on the steps. See that now the process gets a little bit easier in the way that we go more straightforward to find what we want and not going around trying to do explanations. Okay, so that's what you are going to do here, and that's why you want to practice. You want to practice here because you want to be able to do this mechanical process without thinking, okay, without going through all the steps. Richard, yes. Okay, Richard. Are you good with the last number? Do you want me to go into the entire process, or just how I get the depressed equation? Okay, last part. So once you got to this step, this guy here is going to be just the remainder. You are not going to use it. The only thing that you are going just to use it to confirm that you have a 0. 0 there as the remainder. The number that you use here is indeed a 0. Now, these numbers that are here are the coefficients. Okay, so now you are going to take these numbers here, and these numbers are here. Well, what is there? I guess if I copy and paste, it will be better. Oops. Okay. So 0, 0, -4. Come on. And -6. Okay. So you go and take those numbers in the same exact order as you put them below, right? Or any other part on the paper. Now In the same order, you are going to add the variable of the polynomial and then the exponent. You are going to start with the exponent that is one value less than the original one. The degree of the original equation was 4. That means that the next one, the depressed equation, in this case, is going to be 1 degree less. That is going to be 3. So now you have x cubed here, then plus that coefficient, x squared, then that coefficient is negative, so minus 4 and x with the exponent of 1, because then you want to go in order 3, 2, 1, decreasing the value of the exponents. And that is how you get the depressed equation. Okay. Let me do this one because we have time. Okay, let me do this one. Okay, you now have seen how we did the process with a degree of 4. If we wouldn't have rational zeros in the depressed equation, we would just do the same process, total of zeros, 3, least of possible rational zeros, 1, 0, depressed equation to get a quadratic equation. But unfortunately, because this depressed equation does not have any rational zeros, we are going to stop there. Okay? Now, let's now do this one, which is a degree of 3, and this exercise, you will see, this is important in our class. The exercise is going to guarantee you that there's at least one rational zero. If there's at least one rational zero, then we can proceed with the entire process. All right? All right. Step number 1. Let's do this one together. How many zeros? How many zeros? 3. Degree is 3, 3. These zeros could be all rational zeros or complex zeros. At least we know that there is one rational zero. Step number 2. List of possible rational zeros. What are the values that we need to take into consideration? What are the values to get the sorry, let me put this. Okay, what are the values that we need to take into consideration to create the list of possible rational zeros? The constant. So we have -2. And the leading coefficient, which is 5. The constant is represented with the variable p. Okay. And phi is represented with q. P over q. I always mix the letters, but if just let me double check that I'm using what the book says. P over q. P over q, yeah. Okay. Factor of -2 and factor of 5. Okay, 1 and 2, they are prime numbers, both, and 1 and 5. Now let's do the combination. P over q. Okay. I'm just doing something that is not quite formal, or not necessarily correct, but because I don't want to put plus and minus on all my elements, plus and minus in front of the curly brackets, to tells me, and if you do this on your test, that's okay, and because I'm going to understand, that's tell that any element inside this set is the positive and the negative value of it. So 1 over 1 is 1. 1 over 1. 2 over 1 is 2. 1 over 5 is 1/5. And 2 over 5 is 2/5. So in total, we have a possible of 8 rational zeros because the plus and minus. 1, 2, 3, 4 times 2, 8. 1 rational zero. And then we are going to do the graph. And the graph of this exercise is five, 3 minus 7x minus 2. Okay, so this, if I wrote it correct, okay, this one has the 3 zeros are real zeros. Okay, I think that we are seeing here 0.6. Let me find the decimal. Help me on, can you give me the decimal of 1 over 5 and 2 over 5? What is the decimal values? Can you do that and put those values on the chat? 1 over 5. What is the decimal representation of 1 over 5? It's 0.2. And 2 over 5. 0.4. Okay. So what we are seeing there is the one rational zero, and that rational zero is negative 2 over 5. Okay, I think we are going to be in the same Okay, I know what we are going to do here. We are going to be able to find all those zeros. Okay, we have 2 rational zeros. This exercise is important because we have two irrational zeros, and just 1 rational zero. Okay, how we are going to find those irrational zeros, you are going to see, and this is important. This is an important exercise. Okay, so from the graph, we know that the 0 is going to be negative 2 over 5. That is the only rational 0 that this graph has. The other 2 are irrationals. You might wonder at this point, how we are going to find that? Well, because we started with a degree of 3 degree, we are going to be able to find those other 2 irrational zeros. Let's start with this one. We know that the linear factor from this one is going to be 2 over 5. Okay? And here we are going to practice again how to do the synthetic derivation. So the depressed equation. negative 2 over 5. Okay, and let me grab this because this is what we need. Okay, focus on the coefficients. You need to make sure that you have all the coefficients available. So 5, then 3, 2, so negative 3, then 2, 1, so we have negative 7, and negative 2 is the constant coefficient. So we have all the coefficients there. Now, going down, we add. So 5. 5 goes directly there. Going up, we multiply. Multiply this times this. So negative 2 times 5, negative 2 over 5 times 5. And we cancel this, and we got negative 2 here. Okay, going down, we add. And what we are getting here is negative 5. So now we are going to do negative 2 over 5 times negative 5. We cancel this, 2 negative, then we got positive 2. Okay, because these two negatives cancel each other. Going down, we add negative 5. Negative 5 times negative 2/5. We cancel this, and we got 2. Positive 2. Going down, we add, and here we have our friend 0. That's important because that is the remainder, and the remainder is telling us that yes, indeed, negative 2/5 is a 0. Now, what are we going to do with this 5? We are going to get the depressed equation. So what is our depressed equation? You are going to take these numbers directly in the same order. And we went from a degree of 3. That means that now we are going to start here 5x squared. The negative is here. So I'm going just to simplify as minus 5x, and then we have another negative, and I'm just going to simplify just minus 5. All right. So in the previous one, because we reached a degree of 3 depressed equation, and that depressed equation contains non-rational zeros, then we stop there because there we don't have other techniques. But here, things are different. Now, we are working with a quadratic equation, and we have two options. We could find, if possible, by force, those two linear factors, right? We can find those two linear factors, or we can use our famous quadratic equation to get those zeros. Okay, and that's why here in this exercise we can continue working, because we have reached a quadratic equation and we have methods and techniques to work with this one. All right, so let's start with factorization by force here. So the first thing that you will notice here is that you can factor out 5. Okay, so then you focus only on x squared minus x plus 1, and let's see if we can get two linear factors. And this is by trial and error, okay? What I'm doing is just trial and error, finding two numbers that multiply to 1, to negative 1, and so I just by at this point, because we know from the graph that the other zeros are irrationals, it means that we are not going to be able to find those numbers by force here, because those are irrationals. So there's no way to do this type of factorization of this quadratic equation. And that makes sense with the graph. They are irrational numbers. We are not going to think of irrational numbers. We are not going to come up with irrational numbers that multiply to -1, and when we add, we got -1, right? So we stop there because this route is not going to help us. Okay? In your test or in your exercise, you are going to reach out routes that are going to be at that end. Do not feel bad about that. Just, okay, this route is not the one that is going to help me. Let's go to the other one. And here, with the quadratic equation, we can find those irrational zeros. So a good rule of thumb, if you are comfortable with the quadratic equation, use it always, because it's going to give you always a solution. Doesn't matter if it's imaginary or not. Irrational, rational, it's going to always give you a solution. This is 10, sorry. So this is going to be 25 times square root of 5, all this over 10. So square root of 25 is 5. All this over 10. We can factor out. Okay, so here on the numerator we have two terms, 5 and the other one 5 times square root of 5. We can factor out 5. We got 1 square root of plus minus square root of 5, all this over 10. Because we have to factor here now in the numerator, we can cancel this 5 with this 10. So our result becomes those are the two irrational zeros that we are seeing here. Negative 0.623 and positive 1.616. Okay, we can confirm that. We can go to our calculator and let's make sure that yes, indeed, those values are those. Can you help me with the decimal representation of this? Okay, I will do it as well, but I want you to do it so we can agree on the number that we are getting. Okay, I'm getting when we go to the route of addition, I'm getting to 1.618, and when I subtract, when subtracting, I'm getting, and I believe those are the numbers that we saw on the graph. So, how are you going to put the numbers here? you're going to write -2 over 5 using this, and then you can use the plus and minus if I'm not wrong. Then you can write this. And those are the 3 zeros of our polynomial here. One rational zero, like the exercise guaranteed, and 2 irrational zeros. Okay, in this scenario, in this situation, we were able to find the 2 remainder irrational zeros because we reached a quadratic equation. The difference equation is a quadratic equation. We can use the quadratic formula. Alright. So I believe you are tired right now, but at least I have covered the most important concepts of unit number 6. We have 8 more minutes until we finish our section of morning session. But if you have questions, I'm here available. If you want to more practice, I have more exercises that we can go over and practice. If you still have doubt or question about what I just said, just let me know and we can go over that, okay? So I'll stop here at the recording.